So in this lesson, we're going to start with the concept of the binomial theorem. We're going to look at some interesting phenomena, some number trees that turn out to have some very practical applications for us. And we're also going to work with a little bit of nomenclature. We're going to be using the concept of combinations very frequently in this unit. And what we're going to find is we used to write C 4, 2, and that still is a valid representation. But for the purposes of what we're going to be doing in this unit, to save ourselves some handwriting space, C 4, 2, we can write as parentheses 4, 2 with no underscore. Don't turn it into a fraction or anything. That is the same terminology. A 4, 2 like that is the same as a combination 4, choose 2. In general, C, N, comma, R can now be written as NR. Exact same thing. So just tuck that away. The second piece we want to talk about is something called Pascal's triangle. It was a thing found by a mathematician named Pascal many, many centuries ago. It turns out that this triangle and this structure has a great deal of linkage to what we're going to see in a few moments. Now, the way the triangle worked is you run a series of ones down the left and right side of the triangle, and then you fill in the rest of the row with numbers using the following scheme. You take, to ever build a new number, you take the sum of the numbers immediately to the left and the right. So where does this 2 come from? 1 plus 1 equals 2. Where does this 3 come from? 1 plus 2. Where's that 3 come from? 2 plus 1. So I'm going to build another row. So I'm going to drop down a 1 to build my row 5. 1 plus 3 equals 4. 3 plus 3, 6. 3 plus 1, 4. And then I just build my 1 for my outside row. Let's do a couple more while I'm at it. 1. Here comes my next row. 5, 10, 10, 5, 1. That became my row 6. Do something like that just so we can see the breakout. And let's do a row 7 while we're here. 1, 6, 15, 20, 15, 6, 1. And that would be a row 7. So it's a pretty cool, as I say, phenomenon. It has a lot of application for us. But let's do one more thing first, just working with our calculators. Here are a series of combinations, all starting with a 4, picking from 0 through 4. So I'm going to call this going forward, I'll just call this a C40. Well, that value is equal to 1. A 4, 1 is equal to 4. 4, 2 becomes 6. 4, 3 equals a 4. 4, 4 equals a 1. And you'll notice matches perfectly with one of the rows in Pascal's triangle. Now, if you happen to do it, if you did 5, 0 through 5, 5, you'd find out that the answers are 1, 5, 10, 10, 5, and 1. So it turns out that the way the combinations work sync very closely with Pascal's triangle. And then, from an algebra standpoint, there's some very interesting conclusions that fall out of this, and this becomes the binomial theorem, and we'll talk about the concept of a binomial expansion. So, a plus b to the power 0 is simply equal to 1. Maps to the first row, the coefficient, that's just 1. A plus b to the first power is the same as a to the first power plus b to the first power. 1 times a1 plus 1 times b1. 1, 1. Matches up nicely. A plus b squared when we FOIL it out. A squared plus 2ab plus b squared. What are the coefficients? 1, 2, 1. Again, matching perfectly. A plus b cubed. A cubed plus 3a squared b plus 3ab squared plus b cubed. Coefficients. 1, 3, 3, 1. Again, a perfect match. So let's do something. I'll show you what the other expansions look like very quickly. Let me just kind of fold this just to do a couple more. And you'll see, if I went out and you hand multiplied all these, fortunately you didn't have to do that. What do you notice? Same structure. I can see the triangle again in looking at the coefficients. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. They map perfectly to rows of the triangle. And this is what I would get if I foiled this thing out, combined like terms, added like terms, all that lovely stuff. I'd come up with these types of answers. So, real quickly, we'll do a little bit of work. I'm going to copy sum of what I had for a plus b to the fourth. I'm going to write it up here. You'll notice I have a to the fourth. I had a cubed, oh, pen giving out, sorry. I had a to the fourth, a cubed b, a squared, b squared, a, b cubed, b to the fourth. And then what do I also notice? That's what the structure looks like. Well, what's a 4, 0? It's a 1. 1 times a to the fourth, 1. What's a 4, 1? Got it as a 4. Hey, look, my second term, plus 4, a cubed b. What's a 4, 2? It's 6, plus 6, a squared, b squared. What's a 4, 3? It's 4 again, plus 4, a b cubed. 4, 4 is just 1, plus b to the fourth. We can use these coefficients as well as a pattern of our variables a and b to get the entire expansion. Let's follow the pattern just a little bit and see what happens. Notice, what are we doing? We're going to do a plus b to the fifth. Let's run through. We have these coefficients. I'm just going to mark them below, and then we'll fill them in up top. Well, if I follow the same pattern I did with the last one, I should go with 5, 0 through 5, 5. Remember, these are all combinations. Here's 5, 4. Here's 5, 5. And we already said if we work them on the calculator, we would come up and find the 5, 0 is 1, 5, 1, 5, 5, 2, working all the way through. So what I'll do very quickly, here's our first one, 5, 0. That's a 1, and then I'm going to have a to the fifth. 5, 1, that value is a 5. I'm going to work backwards now. I'm going to reduce my power by 1. It's kind of how and we'll see this pattern. A to the fourth, b to the first. A 5, 2, we said was 10. I'm going to have a cubed, b squared. A 5, 3 combination is 10, a squared, b cubed. 5, 4 is a 5, a, b to the fourth. Finally, 5, 5, that turns into just a 1, a to the 0, b to the fifth. And I got a perfect answer that matches exactly what you see here. So I have a nice way to represent a plus b to any power, any integer power, positive integer power. When I build it out, what do I have? I have a bunch of combination numbers, and then I have various powers. Let's talk about this. When I read from left to right, if I look at any of these answers, what do I notice? The powers of a as I move from left to right decrease by 1 with each term. What happens to the b power? Well, b was to the 0 here, and it runs all the way to the fifth. It's always increasing by 1. Next piece, if I add the powers of a and b in each individual term, what do they add up to? Well, they add up to, in the bottom row, they add up to 5. Up here, they add up to 4. They always add up to the power of the original exponent. So the sum of the powers in each term of the expansion matches the value of the, I'm just going to say ORRG, orig, exponent. And what's one more thing we notice? How many terms are there in the expansion? Well, a plus b to the fourth had 5 terms. A plus b to the sixth had, a plus b to the fifth had 6 terms. So I take the original exponent and add 1. Knowing this pattern, build a series of combinations that serve as coefficients, build a scheme for my power of my a and my b and their respective powers in each term, and I have a perfect expansion. So we'll move to the second page very quickly. And here you have the binomial theorem, which is exactly what we implemented on the last page. What does it say? A plus b to the power of n. What do we notice? For each term, we have a coefficient. That coefficient is a combination, n, matching the power that we have. And what's the number that we grab in the combination? It runs from 0 all the way through n. What else do we notice? Well, a to the n, b to the 0, a to the n minus 1, b to the first. If I add those powers, they always add up to n with each term. N starts at its highest power, A starts at its highest power, equivalent to whatever the value of n is. It decreases by 1. B starts at the power of 0 and rides all the way up until you get to a value of n. So it's a good system. That's how the theorem works. When I have to work out a problem, here's what I do. I love to work off the fact that each term has a discernible pattern to it. I know that my first term always is going to have a coefficient, a combination of n, 0. And I also notice that this value of 0 always matches the power of b in the first term, b to the 0 power. n1, b to the first power. n2, b to the second. So whatever power, whatever number I see in the bottom of my combination, that's the power to which b needs to be raised. And that really frees me up to build this thing without having to do a great deal of memorization. Once I know what power b has to be raised to, I just figure out what power does a have to be raised to so that the sum of the powers is equal to n. Let's do one very quickly, and we'll work our way through it. We got a plus b to the 6th power. So n equals 6. What else do we know? Well, I got an a and a b. 6th power, I should expect one more term. I should expect 7 terms to come out. Can I start building them? I sure can. Here's what I'll do. As I say, I always start 6, 0. N is 6, 0. It's going to be what? B to the 0 power, which is, I'll go ahead and write it just so we see it one more time. And then it's, okay, well, I need to be, my exponents for a better be 6. A to the 6, b to the 0, because the powers have to add up. What's my next term? Well, there's a plus sign because I'm always adding here. 6, 1. What do? A goes down by a power. A to the 5th, b to the 1st. Let's keep writing. 6, 2. A to the 4th, b squared. Next, plus 6, 3. A to the 3rd, b third, plus 6, 2. A to the 2nd, a to the 6, 2, I'm sorry, my fault, let me fix this. 6, 4, I was counting the wrong way there for a moment. 6, 4, a to the 2nd, b to the 4th, plus 6, 5, a to the 1st, b to the 5th, plus what's my last piece that I'm going to come across? It's a 6, 6, a to the 0, b to the 6th. So I can work my way through that very quickly. A 6, 0 becomes 1. That's first term is simply a to the 6th. A 6, 1 is 6 plus 6, a to the 5th, b. A 6, 2 is 15. What comes next? Plus 15, a to the 4th, b squared. A 6, 3 is 20 plus 20, a cubed, b cubed. 6, 4 is 15, a squared, b to the 4th. 6, 5 is a 6, 6, a, b to the 5th. And a 6, 6 is simply 1, b to the 6th. There's my expansion. It worked quite nicely for me.